Okay, Srikant, Shiva, now it's coming. Are you hearing me now? Okay, thank you. Okay. So what is the price for the Plus and Iconic subscription? The Plus subscription is available for 12 months, 18 months and 24 months. The Plus, that is for 12 months, Plus subscription fee is the 27,225 rupees. Okay, for 18 months, the fee is the 34,650 rupees. For 24 months, the fee is the 39,600 rupees. Okay, and Iconic subscription, the fee is available. The fee is the 45,225 rupees. Okay, for the 24 months. Okay, it is a 66,600 rupees. This is the fee structure for the Plus and Iconic subscription. Okay, all of it clear now? Yes. Okay, listen. In previous class, we had discussed about three-phase transformers. What are the three-phase transformer connections, and also the vector group analysis of the three-phase transformer. Okay, how do we find out vector group analysis of three-phase transformer? We have discussed that is the, so one is the 0-degree connection, second one is the plus or minus 30-degree connection, and third one is the 180-degree connection. Okay, fourth one is a 180-degree plus or minus 30-degree connection. So this part we have discussed. Okay, 0-degree connection is a possible by using delta delta or the star star three-phase transformer. The plus or minus 30-degree connection is a possible by using so delta star three-phase transformer, or okay, here is a, or this is a star delta three-phase transformer. So 180-degree phase the can also possible in the delta delta three-phase transformer or star star three-phase transformer. Okay, 180-degree plus or minus 30-degree connection is also possible the in delta star three-phase transformer or the star delta three-phase transformer. So this complete discussion, okay, we know that that is a vector group analysis of the three-phase transformer. So this part we have discussed in the previous class. Okay, all of it clear now? So today we will discuss about one more important topic, that is a parallel operation of the transformers here. So what is the meaning of parallel operation? So when two transformers are said to be in the parallel, okay. So this is the supply side, okay. This is the transformer A. So this we can say that the transformer A, and this is a transformer B. Okay, two transformers are connected in the parallel. So it is a transformer A. Okay, this is a A1, okay, terminal. Suppose, okay, this is a transformer A, the small capital A1, and this is the A2 terminal. So now the secondary side, it is a small A1 and the A2 terminals like. Similarly, this is the transformer B. Okay, this is the transformer B. So it is the B1 and the B2 terminal. So this is the capitals, the primary secondary side. So B1 and the B2 terminals here. Otherwise transformer A and the B1 and the B2 terminals. Okay, like. So what it means, see the A1, the positive, or otherwise if we take this a positive and negative supply, and the load side also positive and the negative supply here. So this is the positive and the negative supply. So what we conclude here, so primary windings are connected to the common supply and secondary windings of the two transformers are connected to the common supply. So this is in case of, okay, in case of single phase transformers, okay, the single phase transformers here. Okay, all of you got it, my point? So primary windings are connected to the common supply, and whereas secondary windings are connected to the common supply. So in case of the three phase transformers also, then what will happen? See, in case of three phase transformer, so let us assume this is the common supply side. Okay, it is the supply side of the transformers, and this one is a load bus bar or load side of the transformers here. Okay, got it, fine? So this is the A phase, B phase and C phase. Now similarly here we can take A phase, the B phase and C phase, and this one is also the A phase. Okay, here is a similar A phase and B phase and C phase terminal. So here is also the primary winding terminals are the transformer A. The primary winding terminals of the two transformer connected to the common supply side, and secondary winding terminals are connected to the common supply side. So that what we conclude, so whenever the primary winding terminals are connected to the common supply side, and whereas secondary winding terminals are connected to the common load side, then the transformers are said to be connected in parallel. Okay. Okay, all of it clear now? Okay, whenever this is when parallel two transformers are connected in the parallel, when primaries are connected to the common source, primary winding terminals are connected to the common source, and whereas secondary winding terminals are connected to the common load. Okay, all of it clear? Is that clear, everyone? Okay, Nageshwar, Pavan, Shiva. So what are the conditions to be satisfied to connect the transformers are in parallel? So there are the two types of the conditions. That is the necessary condition to connect the transformers are in parallel, and second one is a desirable conditions to connect the transformers are in parallel. So what are the necessary condition? So necessary condition is required to this is a to connect the transformers are in parallel, and desirable conditions are required to get the successful operation of the parallel operation of transformers here. So first one, the what are the necessary conditions? Okay, here necessary conditions to connect the transformers are in parallel. Okay, so first condition, the condition one here. So this is the first case one we have discussed about the for the single phase, okay, transformers, okay, per single phase transformers. So what are the conditions to connect the transformers are in parallel? So first condition is the polarity of the two transformers must be same. Polarity of the two transformers the must be same. Okay, same here. Suppose here in this example, see here the in this example here. So this is the dot. A1 is a dot and A2 is a undotted. Similarly, A1 is a dot and A2 is a undotted. Similarly, the transformer B also, B1 is a dot and these two are connected to the positive supply and these two are connected to the negative supply here. Now similarly, these are the connected to the positive supply, these are connected to the negative supply. So that first condition to connect the transformers are in parallel. So that is the polarity of the two transformers must be same. Okay. So second condition for single phase manner. So that second condition is the voltage, okay, rating of the two transformers. Voltage, the rating of the two transformers the must be the same. So this is a second condition, that is a necessary conditions. Okay, all of it clear my point? Polarity of the two transformers must be same, and second one, voltage rating of the two transformers must be same. That is the voltage rating of the transformer A, it must be equal to the voltage rating of the transformer B. Okay, so suppose for example point, so this is a transformer A. Okay, transformer A. So voltage rating is a 400 upon the 200 volts transformer. Okay, 200, and the transformer B, okay, also, so it is a 400 upon the 200 volts transformers. So this is the voltage rating. If not same, if it is not satisfied, then what will happen? The circulating current flows between the primaries of the two transformer or secondaries of the two transformers. So which may damage the windings of the transformer. That's why, so what is the necessary condition? Voltage rating of the two transformers must be same. Okay. All of it clear now? For single phase transformer, these are the conditions. Now similarly for three phase transformers, okay, for three phase the transformers. So what are the conditions, necessary conditions to connect the transformers are in parallel? Okay, first condition is the same. So that is the polarity of the two transformers must be same. So this is the polarity of the two transformers must be same. Okay, got it? And second one is the voltage rating of the transformers that must be same. So got it, point? Second one is also the same. The voltage, the rating of two transformers must be same. So example point, okay, here. So this is the voltage 33 by 11 kV transformer, and the transformer B is the 33 by 11 kV transformer. And third one is a, okay, phase sequence of the transformer. Okay, so in addition to this, in case of the three phase transformer, the phase sequence of the two transformers, the frequency of the two transformers, okay, must be the same. Okay, these are same phase sequence. So both transformers should have the same positive phase sequence only or negative phase sequence only. Okay, like so generally we can connect positive phase sequence of the trans. Both are ABC phase sequence only. And the fourth one is the phase displacement. Okay, phase the displacement between the two transformers. The between two transformers, the must be equal to 0. Must be the equal to, okay, equal to 0 here. So this is a very important part. So that is a phase sequence of the two transformers must be equal to 0. The in the vector group we have discussed what is the phase displacement between the primary line voltage and secondary line voltage. But here phase displacement between the two transformers must be equal to 0. Suppose in this diagram, the here, so this is the transformer A 132 by 33 kV. Okay, transformer A 132 by 33 kV. The capacity is the 50 kVA and percentage impedance is the 12.7 and vector group is a YD1. So transformer A is the transformer A. So that is the 132 by, okay, 132 by 33 kV. Okay, 32 kV. And vector group of, okay, vector group, so that is equal to, so it is a YD, okay, YD1, okay, YD1. YD1. So next one, transformer B, the voltage, the ratio, this is the transformer B as the voltage ratio of 132 divided by 33 kV. So next one, the vector group is equal to, so this vector group YD1. So it is also YD1 means it is a plus 30 degrees and this is also plus 30 degrees. So that phase displacement between these two transformers is equal to 0. So that you can connect these two transformers are in parallel. Okay. Pawan, what's your question? What is the application of parallel operation? Okay. Application means, suppose if we use the only one single transformer, we cannot transfer the more amount of power from the source to the load. Suppose if we use two or more transformers are connected in the parallel, we can transfer the more amount of power from the source to the load. Okay. And second one is there is one more. If only one transformer in the line, if any fault occur, we cannot transfer the power from source to the load continuously. So if two or more transformers are connected in the parallel, if any one of the transformer gets failed, then what will happen? You can transfer the power continuously from source to the load without any disturbance or without any discontinuity. So that is the reliability of the power system can be increased. Okay. And one more advantage, or that is suppose only one transformer is there, it is continuously operated, then what will happen? Lifetime of the transformer will be decreased. So two or more transformers are operated in parallel. So with lightly loaded condition, then what will happen? Or off loaded condition. So lifetime of the transformer can be increased. Okay. So this is the very important. Phase displacement between the two transformers must be equal to 0. Suppose we have a connection, sometimes we have a questions. So there is the type of the transformer A. Okay, this is the type of the connection transformer A. And second one is a transformer. Okay, it is a transformer B, the transformer B. So now the phase displacement between the two transformers, the phase, the displacement, the between two transformers, okay, two transformers here. So now whether these transformers are connected in parallel or not, just verify whether transformers are connected in parallel, in the parallel or not, or the not here. So this is the okay, first one. So one of the connection, the transformer 1 is a delta three phase transformer, and it is also delta three phase transformer. So now what is the phase displacement between the this one? Suppose it is a delta will get 0 degree, okay, 0 degree minus the 0 degrees, so that you will get, so phase displacement is equal to, okay, it is a 0 degrees only, okay. So that this is the possible delta transformer, two delta transformers are connected in parallel. And second one is so one is transformer A is a star connection, and transformer B also star connection. So now tell me what is the phase displacement between the here? So it is a 0 degree connection and it is also 0 degree connection. So therefore what is the phase displacement? It is equal to 0. So that these two transformers are connected in parallel. Okay. And next one more connection. So that is the delta star three phase transformer. And the another one is, this is the delta three phase transformer, and another transformer is a star three phase transformer. So both are 0 degree connection. So here 0 degree displacement between here 0 degree connection. So now what is the phase displacement? So it is equal to 0. So other way also we can find, okay, both are, so it is a 180 degree connection and it is a 180 degree connection. So now it is equal to that 0 degree zone. So these two transformers are connected in parallel. Okay, got it, fine. And next one more is a fourth one. So one is the delta three phase three phase transformer, and other one is the delta star three phase transformer. So one is the 0 degree connection and other one is a plus or minus 30 degree connections. Okay, plus or minus the 30 degree connections here. So that you will get minus or plus 30 degrees displacement. So these two transformers cannot be connected in parallel. Okay, all of you clear my point? The power. And fifth one is a fourth one. So transformer A connection is a star, okay, star. And transformer B connection is a delta star. Now verify phase displacement between these two here. Star three phase transformer is a 0 degree connection and delta star three phase transformer is a minus plus or minus 30 degree connection. So that you can write minus plus or minus 30 degrees. So whether these two transformers are connected in parallel or not, so we cannot connect the transformers are in parallel. Okay. And the sixth one, suppose if we take sixth connection, so one is the delta star. Okay, one is a delta star. Suppose it is a very important one is the delta star connection. Another one is also delta star. Okay, so if delta star so one is a plus or minus 30 degree connection. The minus of the plus or minus 30 degree connection, so that it is equal to 0. So therefore, this connection is a possible in the parallel. So these two transformers are connected in parallel. And one more is also very important. See, one is a delta star and other one is a star delta three phase transformer. The transformer A connection is a delta star and transformer B connection is a star delta. So one is a plus or minus 30 degree connection and other one is a the minus, suppose if delta star is a plus 30 degrees plus or minus, then star delta what will happen, the minus are plus 30 degrees, okay, minus are the plus the 30 degrees here, so that it is equal to phase displacement 60 degrees here. So now therefore these transformers are not connected in parallel, okay. And next one, and one more connection, okay, one is the eighth one, so one is the dy1, okay, dy1, and other one is also the other one is dy11. So dy1 and dy11, so dy1 is nothing but plus 30 degrees, okay, and dy11 is the here minus this, dy1 is a plus 30 degrees, dy11 is a minus of minus 30 degrees, so that it is equal to 60 degrees. So these two transformers are cannot be connected in parallel. And one more connection, if I take, suppose it is a dy, the dy 30 degree, okay, 30 degree lag, 30 degree lag, okay. Next other one dy 30 degree lead, okay, 30 degree lead is there. So therefore if it is there 30 degree lag means, so that is a plus 30 degrees, okay, 30 degree lead in the means minus 30 degrees. Now what is the phase displacement, it is equal to 60 degrees here. Now verify here, so this is a 60 degrees, so that these two transformers are cannot be connected in parallel. So it is a very important for 1 mark point of view. So any two connections are given, whether these two are, okay, connected in parallel or not, okay, this is one of the question in a computer exam. In seventh case, delta star, no, actually if delta star three phase transformer connection, if we get plus or minus 30 degrees, okay, if delta, seventh case delta star, so if it is star delta, okay, if it is a star delta, then we will get minus or plus or 30 degrees. So if we take a vector group, vector diagrams point of view, you can answer this. So if it is a delta star, okay, delta star, suppose if we get dy1, okay, dy1, suppose if we connect only reverse connection, that yd, then there is a possibility to get the dy11, okay, dy11. So suppose in the delta star there are the 4 possibilities to get the phase displacement. In the previous class we had discussed. So if delta star is a 30 degrees and yd will become minus 30 degrees. So if suppose yd is the plus 30 degrees and delta y will become minus 30 degrees. So therefore phase displacement is, just go through my lecture vector group of 3 phase transformer, you will get clear idea about this concept. The previous class I had discussed very clear vector group analysis of the 3 phase transformers. Nageshwar, are you clear now? So now what are the desirable conditions? Okay, this one is a, so next one, the desirable condition to connect the transformers are in parallel. Desirable conditions to connect the transformers are in parallel. So now tell me what are the desirable conditions. Actually necessary conditions are required to connect the transformers. Transformers are in, these are the must to be satisfied. Otherwise there is a circulating current between the two windings of the transformer which may damage. So desirable conditions are required to get successful operation of the parallel operation of transformers here. Okay, first desirable condition, okay, this is the first desirable condition. Star delta lo opposite terminal తీసుకుంటే 1 possible అవుతుంది కదా. Okay, స్టార్ డెల్టాలో వాట్స్ క్వశ్చన్. స్టార్ డెల్టా నువ్వు ఇక్కడ మనకు తెలియదు కదా టెర్మినల్స్ ఏది అనేది. నువ్వు ఆపోజిట్ టెర్మినల్స్ అని మెన్షన్ చేయలే కదా మనకు. సపోజ్ ఇక్కడ డెల్టా స్టార్ ఇచ్చిండు. సో నెక్స్ట్ జస్ట్ ఓన్లీ స్టార్ డెల్టా స్టార్. ఇయర్ ద డెల్టా ఇస్ ద ప్రైమరీ, సెకండరీ ఇస్ ద స్టార్. But here star delta in the sense terminals are remain same, but the windings primary side is a star and this is a secondary side is a delta, but terminals outgoing terminals are remain same. That's why you will get opposite. నీకు పాసిబిలిటీ ఇవ్వలే కదా. నీకు సపోజ్ ఇక్కడ ఏమని ఇస్తాడంటే నువ్వు టూ వైండింగ్ సపోజ్ డెల్టా స్టార్ అండ్ డెల్టా స్టార్ లో ప్యారల్ ఆపరేషన్ కనెక్ట్ చేయవచ్చా లేదా అని అడిగిన అనుకోండి క్వశ్చన్. నువ్వు ఎలా యాక్సెప్ట్ చేస్తాం? నువ్వు డెల్టా స్టార్ అనేది డెల్టా స్టార్ లో ప్రైమరీ ఇస్ అ డెల్టా అండ్ సెకండరీ ఇస్ అ స్టార్. నువ్వు స్టార్ డెల్టాలో ప్రైమరీ ఇస్ అ స్టార్, సెకండరీ ఇస్ అ డెల్టా. నువ్వు అవుట్ గోయింగ్ టెర్మినల్ చేంజ్ చేస్తలేను నేను, జస్ట్ ఓన్లీ ఇంటర్చేంజింగ్ చేస్తున్నప్పుడు. ఇంటర్చేంజింగ్ చేసినప్పుడు ఏమవుతుందంటే ఇఫ్ డెల్టా స్టార్ ఈస్ అ ప్లస్ 30 degrees, the star delta will become minus 30. Suppose if terminals are given in the diagram, there is a possibility. Suppose నువ్వు డెల్టా స్టార్ తీసుకున్నారు అనుకోండి, దీంట్లో ఎన్ని పాసిబిలిటీ ఉంటాయంటే నీకు ప్లస్ 30 degrees కావచ్చు, మైనస్ 30 degrees కావచ్చు, వన్ మోర్ ఇస్ 180 degree ప్లస్ 30 degrees పాసిబిలిటీ అవుతుంది, మైనస్ 180 degree మైనస్ 30 degrees కూడా పాసిబిలిటీ అవుతుంది. సో నువ్వు డెల్టా స్టార్ లో ఫేజ్ డిస్ప్లేస్మెంట్ 4 పాసిబిలిటీస్ ఉంటాయి. నీకు 4 పాసిబిలిటీస్ లో నీకు అవుట్ గోయింగ్ టెర్మినల్ చేస్తే 2 పాసిబిలిటీస్ వస్తాయి. కానీ ఇక్కడ మనకు అవుట్ గోయింగ్ టెర్మినల్స్ తెలియదు. నువ్వు జస్ట్ ఓన్లీ ఇంటర్చేంజ్ చేస్తున్నాను ప్రైమరీ స్టార్ స్టార్ డెల్టా అని. అప్పుడు ఇంటర్చేంజ్ చేసినప్పుడు ఇప్పుడు ఈజ్ ఏ డెల్టా స్టార్ ప్లస్ 30 degrees అండ్ స్టార్ డెల్టా విల్ బికమ్ మైనస్ 30 degrees. నువ్వు వెక్టార్ గ్రూప్ క్లాస్ నువ్వు అటెండ్ అవుతే తెలుస్తుంది. ఒకవేళ మీకు అటెండ్ కాకపోతే నేను ప్రాబ్లమ్స్ మీకు చేపిస్తాను దానిపైన. ఎస్, నీకు డెల్టా స్టార్ లో వెక్టార్ గ్రూప్ ఎన్ని పాసిబిలిటీ అవుతుందంటే 4 పాసిబిలిటీ ఉంటాయి. అదే డెల్టాలో ఓన్లీ 2 పాసిబిలిటీసే ఉంటాయి. సో ఇక్కడ ద టూ పాసిబిలిటీ కాబట్టి నేను ఏదైనా ఒకటి తీసుకున్నాను. 0 degree కనెక్షన్ 0. నువ్వు అవుట్ గోయింగ్ టెర్మినల్ సేమ్ అని తీసుకుంటేనే బోత్ ఆర్ ఇన్ ద సేమ్. అవుట్ గోయింగ్ టెర్మినల్స్ నువ్వు డిఫరెంట్ తీసుకున్నావు అనుకో, వన్ ఈజ్ 0 degree, అదర్ వన్ విల్ బికమ్ 180 degrees అని మనకి తెలియదు కదా. నువ్వు కన్సిడర్ ఏం చేసుకోవాలా, అవుట్ గోయింగ్ టెర్మినల్స్ అనేవి సేమ్ బోత్ కేసెస్. బట్ నువ్వు ప్రైమరీని ద సెకండరీ సైడ్ ప్రైమరీ ఉంది అనుకోండి, ఇయర్ ప్రైమరీ డెల్టా అండ్ ఇయర్ ఈజ్ అ సెకండరీ ఈజ్ అ స్టార్, బట్ వీఆర్ ఇంటర్చేంజింగ్. ప్రైమరీ ఈజ్ అ స్టార్, secondary is a delta. So if it is interchange, then what will happen? So if the star delta star is a plus 30 degrees, then star delta connection is a minus 30 degrees. If outgoing terminals are same, if it is mentioned that, then we can use that formula. ఓకే నాగేశ్వర్, అర్థమైందా? ఓకే ఓకే, పాసిబుల్ అవుతుంది. కానీ మన క్వశ్చన్ ఎలా అడుగుతాడంటే 2 connections ఇచ్చి వెదర్ దీస్ 2 transformers ఆర్ కనెక్టెడ్ ఇన్ ప్యారలల్ ఆర్ నాట్. దట్ ఈస్ ద క్వశ్చన్ పాయింట్ ఆఫ్ వ్యూ. నువ్వు అప్పుడు నీ కనెక్షన్ ఈ డెల్టా డెల్టా అని ఇట్లా ఇస్తాడు, లేకపోతే some connections is which transformer connection is not possible to connect the transformers are in parallel. అలాంటి అన్నప్పుడు మనకు డెల్టా డెల్టా తెలియదు కదా, అవుట్ గోయింగ్ టెర్మినల్స్ అనేది తెలియదు. మనం ఇక్కడే అనాలిసిస్ చేయాలి. నువ్వు డెల్టా స్టార్ అనేది 30 degrees అంటే స్టార్ డెల్టా కంపల్సరీ మైనస్ 30 degrees ఉంటాయి. నువ్వు అవుట్ గోయింగ్ టెర్మినల్స్ రిమైన్ సేమ్ ఉంటాయి. ఓకే, so now what are the desirable conditions to connect the transformers are in parallel? So first condition is the KVA load KVA or KVA shared by the transformers. Okay, so it's directly proportional to or load shared by the transformer. The first condition, the load shared by the transformer shared by transformer, the transformer is directly proportional to its kVA rating. Okay, this is the one of the desirable condition. If it is possible only if given that output terminals are different from the each other. Yes, if it is a possible only, suppose if it is mentioned, we can analysis like that. So what are the desirable conditions? Load shared by the transformer is directly proportional to its kVA rating. So what it means here, IKVA rating transformer, suppose that for example here, so this is a transformer which has high kVA rating, IKVA rating as compared to other transformer, which has high kVA rating as compared to other transformer should share the load of low load power, should share low load kVA. Okay, sorry, this is the high, so should share the load of high load kVA here. So it means that, so transformer IKVA rating, transformer which has IKVA rating as compared to the other transformer should share high load kVA. Similarly, the transformer, okay, this is the similarly the transformer which has the low kVA rating, low kVA rating, the should share the low kVA, load kVA, the load kVA here. So this is nothing but load shared by the transformer is directly proportional to its kVA rating. So now question is, how do we obtain this condition while doing the parallel operation? Okay, this is a how do we obtain? Okay, how do we get? Okay, how do we get? So how do we get, or how do we satisfy this condition, or how do we satisfy this condition while doing the parallel operation of transformers here? So suppose here the impedance of the transformer, so impedance in ohm, so that is the ohmic impedance of the transformer. If ohmic impedance of transformer is inversely proportional to its kVA rating, its kVA rating, so then the above condition is possible. Above condition is a possible here. So what it means, above condition is possible. All of it clear point. So if ohmic impedance of the transformer is inversely proportional to its kVA rating, then the above condition is a part. That means load shared by the transformer is directly proportional to its kVA. Suppose if it is not possible, then what will happen here? Okay, what will happen? So one transformer is operated in the overloaded portion and one transformer is operated in the underloaded portion. So which is undesirable. That's why it is called as the desirable condition of the parallel operation. Okay. This is the condition 1. So what it means, see, so for example, the impedance of the transformer, impedance is inversely proportional to its kVA rating. So there are the two transformers are there. So impedance of the transformer A, okay, ohmic impedance of the transformer A. So that is the ohmic impedance of the transformer B is equal to, okay, impedance of transformer is equal to the KVA rating of transformer B. So divided by KVA rating of the transformer, KVA rating of transformer, the A here. So now simplify this one, the impedance of ohmic impedance of the transformer A, the into KVA rating of the transformer A. So equal to the impedance of the transformer B. Okay, this is the impedance of transformer B, the into KVA rating of the transformer B values here. So voltage ratings are both transformer as same voltage rating. So that's why we can write ZA in the ohms multiplied by KVA, okay, ZA in the ohms, the KVA, the divided by the kilowatt, the voltage, okay, the voltage rating of transformer A square, and is equal to the impedance of the transformer B, ohmic impedance, and KVA of transformer B, the into, that is a voltage rating of the transformer B square here. So now voltage we know that here. So we know the here VA is equal to VB. So what is the reason? The voltage rating of the two transformers are equal. That is a necessary condition. So what it means? Okay, ohmic value KVA by voltage square. So this is equal to the impedance, per unit impedance of the transformer A. So equal to per unit impedance of the transformer B value here. Suppose if per unit impedance of the transformer A equal to per unit impedance of the transformer B, so then the here transformer will share the load directly proportional to its KVA rating. Okay, this is nothing but per unit impedance, per unit impedance of the transformer A, and this one is the per unit impedance of the transformer B. Okay, when per unit impedances are equal, so then what will happen? So when per unit impedance of their respective KVA ratings are equal, so when there is a load shared by the two transformers are directly proportional to its KVA rating. Okay, and next one, the second desirable conditions. Okay, desirable condition. So X by R ratios of the two transformers. X by R, the ratios of the two transformers should be equal. Okay, equal to operate at the load power factor. At load power factors. Okay, load power factor here. Suppose let us take the case 1 here. The case 1, X by R ratios are equal here. Then X by R ratios of the transformer A is equal to the X by R ratios of the transformer B. Okay, case 1. So then what will happen? Let us take tan inverse. The tan inverse of X by R ratios of the transformer A is equal to the X by R ratios of tan inverse of X by R ratios of the transformer B. So now tan inverse X by R in the sense that theta A is equal to the theta B here. So what is the theta A and theta B? Suppose let's take cos on both sides. The cos theta A is equal to cos theta B1. So cos theta B. So that is the power factor of the transformer A. Power factor of transformer A. And this one is a power factor of the transformer B. So if X by R ratios are equal. Suppose in the case 2, if X by R ratios are, case 2 here, if X by R ratios are unequal, then what will happen? See, suppose X by R ratios of the transformer A is a greater than the X by R ratios of the transformer B. So then what will happen? So take both sides take the tan inverse on both sides. So tan inverse of x by r ratios of the transformer A greater than tan inverse of x by r ratios of the transformer B. Okay, got it? So now this is equal to theta A greater than the theta B. Okay. So now this is there. When theta is greater than the theta B, so cos function will what will happen? Cos theta A less than the cos theta B values here. So what we conclude from this discussion, so when if x by r ratios of the transformers are equal, so both are operated at the load power factors. Otherwise, what will happen? The transformer which has the low x by r ratio, okay, transformer which has low x by r ratio, so then it will be operated the superior power factor of the load. The transformer which has the high x by r ratio will operate inferior power factor of the load, which is undesirable. That's why it is treated as a undesirable condition. So when x by r ratios are, okay, when x by r ratios of two transformers are unequal, then what will happen here? The transformer which has low x by r ratio will operate at superior power factor of the load. Superior power factor of load, and transformer which has high x by r ratio will operate at inferior power factor of the load. Inferior power factor of load, which are undesirable, which is undesirable. That's why this condition is called as a undesirable condition. What is superior means? It is a greater than, for example, so here if load power factor here, example, load power factor is equal to 0.8. So if it is a x by r is a low, if x by r is a low, so then what will happen? It is operated, the transformer A x by r ratio here low, so it is operated at 0.9 power factors. Okay, suppose if x by r ratio of the transformer B is a high, so it is operated at the 0.7 power factor. Superior means greater than, okay, inferior is the less than. Inferior, okay, less than the load power factor. Superior is the greater than the load power factor. Okay, all of it clear now? So these are the desirable conditions and also necessary conditions to connect the transformers are in parallel. Okay, very important. These are the necessary conditions to connect the transformers are in parallel. Okay, next one. So these are second case. Second one is the desirable conditions to connect the transformers are in parallel. So first condition is a load shared by the transformer is directly proportional to its kVA rating. So how do we get this condition? Impedance of the transformer is inversely proportional to its kVA. Then the load shared by the transformer is directly proportional to its kVA rating. Otherwise, the one transformer will be operated overloaded condition, other transformer will be operated in the underloaded condition. So which is undesirable. Okay. And next condition, x by r ratios of the two transformers thus should be equal to operate at the load power factors. Yes, okay. So here ZA is a two transformer A and transformer B. The primary winding terminals are connected to the common source and secondary winding terminals are connected to the common load. Okay, that is a load here. So let us assume, okay, let in this case, okay, let ZA is the impedance of the transformer A. Okay, this is the ZA in the sense it is the impedance of the transformer A. Okay, transformer A. So where ZA is equal to, okay, it is a RA the plus J XA value here. Okay, XA. Similarly, the ZB is a impedance of the transformer B. Impedance of transformer B value here. So how do we get ZB value here? ZB is equal to the RB plus JXB. So a resistance and total equivalent impedance of the transformer A, equivalent impedance of the transformer B. Like so, next one, the here in this case, IA is a okay. There is a parameter IA. So this IA in the sense, okay, it is a the load current flows through the transformer A. So this is the current of transformer A. So current flows through the transformer A and IB is a current flows through the transformer the B value here, the current. So what about the ZL here? ZL is the load current. Okay, load current here. So this ZL is the load current. So now see here IA plus IB is equal to the IA plus IB is equal to ZL. So these two are connected in parallel. Okay. So now here is we have a two condition. What is the load shared by the transformer A and load shared by the transformer B? This is the we have to find out. So we can find in the two ways. Suppose if voltage ratings are equal, the equal voltage ratios, okay, are unequal voltage ratios also. So there is a very important question here. How do we find out voltage rating of the two transformers? All of you clear point? And here is a V2 is the terminal voltage, okay, load terminal voltage. So now the how do we find load shared by the each transformers? Okay. So first case, okay, here is a if voltage ratios of two transformers are equal, then how do we get the kVA shared by the each transformers here? ZA is the complete equivalent impedance, not ZA in the sense equivalent impedance of the transformer A. ZB is the equivalent impedance of the transformer B, not secondary or primary. Equivalent impedance of the transformer A and equivalent impedance of the transformer B. Okay, load is connected to the secondary side. That's why it is a referred to the secondary side parameters. Okay, for example, if voltage rating of the two transformers are equal in the sense, so this is the 33 here, this is the 400 upon the 2000 volts transformer, it is the transformer A. Okay, now transformer B also the same voltage rating 400 upon 400 upon 2000 volts and this also 2000 volts. The voltage rating of the two transformers are equal. Okay. primary side here load shared by the two transformer. Primary side load ఉండదు కదా పవన్, లోడ్ ఎక్కడ ఉంటుంది? సెకండరీ సైడా ప్రైమరీ సైడా? ఓకే సార్, బట్ వై నాట్ కనెక్టెడ్ ఇన్ ద ప్రైమరీ? నువ్వు లోడ్ ఎక్కడ సెకండరీ సైడ్ లో ఉంటుందా, లోడ్ ప్రైమరీ సైడ్ లో ఉంటుందా? Okay, Pawan, are you getting my question? Load is connected to the secondary side, not in the primary side. Am I right? Secondary side. So our topic is load shared by the two transformer. So why we connect, if it is connected to the primary side, how does it shared by the transformers? That is the equivalent impedance referred to the secondary side. Equivalent impedance referred to the secondary side of the transformer A and transformer B. Why? Because it is connected to the secondary side, right? Primary side supply. Okay. So now here, if voltage ratios of the two transformers are equal, okay, equal. So then how do we find out? Okay. So we know that IA is equal to, okay, voltage ratings are equal. So now first tell me the current by using current division principle. Okay, by the current division, okay, division principle, okay, principle, the current flows through transformer A. Transformer A, so that is equal to, so it is a IA here. IA is equal to, in terms of the load current, IL. Okay, it is a ZB by, okay, ZA plus ZB. Okay, ZA plus ZB values. Are you getting my point? By current division, both are in parallel, so that current division principle here, IA is equal to IL ZB by ZA plus ZB. So now both sides multiplied with the EL. So voltage rating are equal. So E multiplied by IA, so is equal to E multiplied by IL. So this is the ZB divided by the ZA plus the ZB values here. Okay, ZA plus ZB. So therefore here, so E into IA and E into IL. E into IA here, the KVA rating. So now it is called KVA shared by the transformer. The KVA, the shared by the transformer A. Transformer A is equal to, it is a E multiplied by IL. So it is called the load KVA. The load KVA, the shared by load KVA multiplied by the ZB by ZA plus the ZB values here. Okay, ZA plus. So this is the KVA shared by the transformer, the A. Okay, if voltage ratings are equal. And what about KVA shared by the transformer B? How do we get KVA shared by the transformer B? So now by current division principles, okay, by current the division principles. So now here is a, we have taken the current flows in the transformer. Okay, current flows in transformer B. Okay, transformer B. So how do we get current flows in the transformer B? By using current division principle here. IB is equal to the total load current IL. Okay, here ZA divided by ZA plus the ZB values here. Okay, ZA plus Z. So now in this case, I here both side multiplied with the E. E multiplied by IB, the is equal to E multiplied by IL, the into ZA by the ZA plus the ZB values here. Now simplify this. Okay, it is a KVA shared by the transformer. KVA, the shared by the transformer B, okay, is equal to the load KVA, okay, load KVA into the ZA divided by the ZA plus the ZB values here. So this is a the this is the kVA shared by the transformer A and transformer B. All of it clear now? Yes, but in the textbook you can derive another way also. Just I am applied here just current division principle. So we know this load current. So we have to find out the current flows in the transformer A in terms of the load current. The current flows in the transformer B in terms of the load current. This is in the case 1. Case 1. Okay, that is if voltage ratings are equal. Okay, ratings are equal. So in this case, okay, here there is a one important note. Okay, here. So notes. Okay, that part we will discuss in the another part. So there is a notes here. In the above equations, okay, here the first one ZA and ZB are, okay, ZB are in ohms, okay, in the ohms are per unit, okay, in the ohms are per unit. Suppose in any problem, okay, in any problem, in the any question, okay, or any problem or any questions. So in any problem, so if ZA, ZB are given, okay, ZA and ZB are given in the ohmic values, given in ohms, then substitute these values in the above formulas directly. Then substitute these values, very important, these values in above formula directly. Okay, suppose if the here is a, if in the any problem or any question, okay, so if ZA, ZB are, ZA and ZB are given in the per unit value, are given in per unit value, okay, per unit values, then don't substitute these values directly. Okay, don't substitute these values directly. These values directly. So first what we have to do here, first find new per unit value, values by considering a common base value, okay, common base value from old per unit value, that is a given per unit values. Okay, how do we here? So this let assume here common base value, so common base KVA. So that is the any one, the transformer KVA, the KVA rating of transformer A or the KVA rating of the transformer B. Okay, anyone you can take. Okay, KVA rating of transformer B here. So that is the, how do we get the formula here to get the new per unit value? So Z per unit, the new is equal to, okay, equal to the Z per unit, the old multiplied by the KVA new. Okay, this is the KVA new divided by KVA old. Okay, so this is the formula. Okay, why we have taken only kVA? There is a voltage ratings are remain same. Voltage ratings, okay, voltage ratings are same. That's why we have to take only kVA with respect to the K. So these are very useful for problem solving. If ZA ZB are in the ohms or per unit, but in this if either ZA ZB are given in the ohms, there is no problem. You can substitute these values in the above formulas directly, so to get the load shared by the each transformer. But if ZA ZB are given in the per unit value, there is a difficulty. So what we have to do here, first to find out the new per unit values, okay, new per unit values by considering a common base kVA, so common base value from the old given per unit values. Okay, so let common base kVA here, each one here kVA rating of transformer A or kVA rating of transformer B. Okay, this is the kVA rating of transformer A and kVA rating of transformer B. So by using this formula, we can get the new per unit values. Yes, all of it clear now? Very important. This is the notes. Nageshwar, Pavan, yes. Okay, very important to solve the problems based on the parallel operation. So next one, case 2. Okay, case 2 here. So how do we get case 2 values? Case 2. So for here, unequal voltage ratios. Unequal voltage, the ratio. Okay, unequal voltage ratios here. So that means your ZA V2 here, for example, point. So one transformer is a 400 upon the 200 volts. Okay, other one is a 400 upon 600 volts transformer. So this is the transformer A and this one is the transformer B here. So these are the unequal voltage ratios. So at this time, so what about the current here? So we know that, okay, this load current. So IA is equal to IA plus IB is equal to IL. Okay, IL values here. So now how do we write this IL? So VIL is equal to, so EMF here V2, okay, V2 minus, okay, VMF E2 minus the V2 divided by, so impedance of the transformer, the V2A, the by, okay, here the impedance of the transformer A. So next one plus the, here is a, this one is a, so we will get either this is the V2B, okay, the V2 of the transformer B. So minus of the V2, so divided by the impedance of the transformer B. So this is equal to, you can write, so V2 of, okay, ZL. So from this equation, find I2, V2, how do we get V2 here? So this is the V2 we can obtain. So this is the V2 by V2 is equal to, so V2, simplify this equation. So V2 is equal to, anybody got it? V2. So this value is equal to the E2A divided by ZA, the plus the E2B divided by ZB. So now it is equal to the 1 by the ZA plus the 1 by ZB, the minus, okay, 1 by ZA plus or 1 by or plus 1 by ZL. Okay, this is the formula to get the load terminal voltage for the common kVA. Okay, And after getting the V2, then find here. So how do we get IA value? Therefore, IA is equal to, so that is a IA value is equal to the V2A minus V2 divided by, so ZA. Okay, V2A divided by Z. So next one, IB is equal to, how do we get IB? So this IB is equal to the V2B minus the V2 divided by the ZB. So we can get the currents. Okay, current in the A, current in the transformer A, current in the transformer B. So next one, how do we get power? So this the power here, active power or the any power. So let us find active power. Active powers. Okay, active powers here. So how do we get the active power? So it is a PA is equal to the active power shared by the transformer A is equal to, so now it is a V2 IA. Okay, IA, the cos of angle between, okay, angle the between the V2 and IA, right? The V2 and IA. So it is a no load voltage. So this is a power, active power shared by the transformer A. So that is a V2 IA cos of angle between these two. So next one, the power B is equal to the V2 IA IB, the cos of angle between, okay, angle the between the V2 and IB. Okay, V2 and IB here. Now similarly, the reactive power shared by the two transformers. Okay, these are the reactive powers. Okay, reactive power shared by the two transformers here. How do we get QA is equal to, that is the V2 IA, the sine of, okay, angle between, okay, angle between, so it is a V2 and IA, right? Okay, V2 and QB, the reactive power shared by the transformer B. So that is a V2 IB sine of the angle between, okay, angle the between the V2 and IA values, okay, I2 and IB values here. So this is about the reactive power. And what about the active power here, apparent power here? So this is the very important. So KVA shared, the apparent power, and it is nothing but the KVA, KVA shared by the transformer A. So right, so now how do we get this power? So that is the KVA shared by the transformer A is equal to the P plus JQ, okay, PA plus the QA, and this one is a SB is equal to the PB the plus JQB here. Okay, this is the form. Other way also we can get, suppose here, so there is a power triangle methods. Okay, here is a power. So now it is a theta A. Okay, it is a power P, Q, and so now this is the S. Okay, S is a required. So now we can write that is a the tan theta is equal to, okay, tan theta. So that is a P by Q. Okay, P by Q here. So now otherwise we can write this function in terms of the S. Are you clear now? P by Q into S. Okay, it is a theta. So now sine function. Okay, sine it is equal to. So that is a, okay, this is a Q by that is S. So now cos theta is equal to the here P by S. So from which we can write. So we can, this one is a, the SA is equal to, okay, this is the only one method. Suppose if you want to find out, if you know the active power here, so then here Q is equal to, the QA is equal to the S into sine theta, or theta is equal to cos inverse P by Q. So these are the formulas to find out the KVA shared by the two transformers if load is unequal. . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . Yes, all of you clear now? So if load, the voltages are unequal like this, we have to calculate. Yeah, that is also correct. But IA we can get, but we required. But we required in terms of the load. SCA is equal to VA into IA. Okay, VA into IA. But so this is the very easy as compared to that one. The load shared by the this SCA in the sense K, when SCA is a SCA is the KVA shared by the transformer A, by transformer A, and SB is a the KVA shared by the transformer B. Okay, so this is the active power and this is the reactive power, and active power and reactive power. If unequal voltages are given, this is the formulas. So this from here, the sometimes we have a question terminal voltage. Okay, it is a armature, that is a currents in the this the current in the A and B, and active power, reactive powers, and also KVA. Okay, so now we will solve some questions based on this concept. So first read this question, all of you. Possible three to three phase transformer connection per parallel operation. Tell me. So first one, delta star, delta star, delta delta, delta star, star star, delta star. Okay, delta star and star star. Okay, which option is given? So see here, option A is given. So it is a transformer A, delta star. So this one is a transformer A. Okay, and transformer, okay, transformer B is there. So now find out the phase displacement. Okay, so now whether transformers are first one, delta star and delta star. So it is a, suppose it is a plus or minus 30 degrees, the minus of plus or minus 30 degrees, so that it is equal to 0. So these two transformers are connected in parallel. And next one, delta delta and delta star. So now tell me this. Okay, here delta delta, delta star, delta delta is a, so that is a 0 degree, the minus of the plus or minus 30 degrees. So that is equal to the minus plus 30 degrees. So it is not possible. So next one, the star star, okay, and delta star. Star star is a 0 degree connection and delta star is a plus or minus 30 degree connection. So now this one is equal to minus plus 30 degrees. So that it is also not possible. And one more is given, delta star and star star. Okay, this is also, so delta star is a plus or minus 30 degree connection, the minus of 0 degrees, so it is equal to plus or minus 30 degrees. So it is also not possible. So absolutely option A is a correct. Like this we have to answer this question. Okay, are you clear now? Next one more possibility question from this concept. Answer this. So this was IAS question, IAS 99. For all other requirements for parallel operation of transformers are fulfilled, Which one of the following pairs of the three-phase transformers with given vector groups can be operated in parallel? Can be operated in parallel. Option A, YD1, YY0. YD1 in the sense, okay, for option A, see, YD1 is a plus 30 degrees, okay, 30 degrees. So now this is the per phase displacement, verify the phase displacement. YD1 is a plus 30 degrees minus of the 0 degrees. YD0, that is a 0 degree only. So now this is equal to the plus the 30 degrees, okay, 30 degrees here. So next one, for option B, the phase displacement is equal to, just verify the phase displacement between the two transformers, okay, two transformers. So that is equal to, okay, YD1 is a plus 30 degrees, okay, YD11 in the sense, so that is a minus of the minus 30 degrees, YD11 is minus 30 degrees, so it is equal to 60 degrees, right? So next, the per option C, the phase displacement between the two transformer, YD6 in the sense 180 degrees, okay, 180, DD6 is the 180 degrees, okay, and dy1 is a minus of plus 30 degrees, so that is equal to how much? 180 minus 30 degrees, it is a 150 degrees. Next one, the phase displacement between the two transformers, okay, dd0 in the sense 0 degrees, my dy11 in the sense minus 30 degrees, okay, now it is equal to plus 30 degrees. So that what is the answer for this question? Yes, here is a given that, so there is a two different connections, okay, YD1 and DY1. So YD1 here, YD, okay, it's both are not in the same, okay, that's why option B is the suitable. Okay, what is the reason here? So this is the YD, suppose, okay, YD, the star delta, okay, star delta, and okay, the delta star, okay, delta star is given for option B. So this is not possible, this is not possible, and this is also not possible, but there is a one twist in the option B, see here, okay, in the option B. So it is not in the same, okay, here initially it is a star delta and delta star. So if star delta is, okay, star delta is a 30 degrees, okay, 30 degree connection, and delta star will become here minus 30 degree connection. So that possible connection here, the can operated in parallel, okay, option B is a possible. Yeah, okay, this one is a YD is a star delta here plus 30 degrees, dy will become, what will happen? Minus 30 degrees. Minus 30 degrees. And but here displacement is given. Okay, here the dy minus 30 degrees. So that minus will become minus, here it is the plus 30 degrees. So that is the 30 degrees minus of plus 30 degrees, it is equal to the 0 degrees. Are clear now? Otherwise, can I explain once again? See, YD1, okay, YD1 is a, yes, I will explain, see, okay, YD1 is a plus 30 degrees, right? Okay, and dy, okay, dy11, so that is a minus 30 degrees. So from this dy11, if I write, so if I write yd, okay, this is the, if we interchange, yd. Okay, yd1. Suppose if I interchange in the connections, okay, in this case if I interchange yd, okay, some this will become, what will happen here, so minus the plus 30 degrees here. So therefore here star delta, the plus 30, the star delta here plus 30. Now here this is the, I am interchanging, okay, this with respect to the first one. So then what will happen, it will, you can also equal to plus 30 degrees. So that is the plus 30 degrees minus 30 plus 30 degrees of minus of plus 30 degrees, so that it is equal to 0. Okay, are you clear now? yd1 equal to dy11 and yd11 is equal to dy11. Yes, that's correct. So yd1 equal to dy11. Okay, that's correct. So our yd11 the is equal to, okay, equal to yd11 is equal to dy1. That's why both are in the same pace, plus 30 degrees and plus 30 degrees. Okay, now solve this question. Two single phase transformers are connected in parallel to share the load of 1000 kVA. Rating of the transformers and their impedances are given as follows. For transformer A 800 kVA, XA is equal to 2 ohms. For transformer B 400 kVA, XB is equal to 4 ohms. Here RA is here, the resistance is neglected. That's why it is given XA terms. So find kVA shared by the each transformer. Okay, how do we answer this question? Here given that the load kVA, okay, load kVA, so that is equal to 1000 kVA. Okay, so now kVA shared by the transformer A. So these two are given in the ohmic values. So that's why you can substitute directly. kVA shared by transformer A. So that is equal to, how do we get? So what is the formula? Okay, load kVA into the ZB by, okay, the ZB by ZA plus ZB values. So here RA is not given, so that neglect. So now this equal to, we can write load kVA is equal to the 1000. Okay, these are given in the ohmic values. So that's why 4 by the, here is the 2 plus 4. Now simplify this, you will get answer. So next one, kVA shared by the transformer B. Okay, so that is equal to load kVA, okay, into, so now this is a ZA divided by ZA plus ZB values. Okay, that is the 1000 kVA, 1000 the kVA into, so here 2 divided by the 2 plus 4. So now simplify this. What is the answer? First one, 8 by, that is a, okay, thousand into 4 divided by 6. Okay, so one is the, this is equal to 666.6 kVA. Good. And this value is equal to the 33 point, okay, 333.33 kVA. Yes. Okay, next solve one more question here based on this same concept. Two single phase transformers are connected in parallel to share the load of 1000 kVA. Rating of the transformers and their impedances are given as shown in the below. For transformer A, 800 kVA, XA is given in the percentage 2%, XB is equal to 2%. So now find kVA shared by the each transformer. Here there is a difficulty. If XA XB given in the ohms, you can substitute directly. But what will happen? These are the given in the year. So given that the given here, given load kVA is equal to, okay, load kVA, so that is equal to 1000 kVA, okay, 1000 kVA. So next one, the XA per unit, XA, the whole value per transformer A, sorry. So XA per unit, okay, XA values, okay, XA is equal to, is in the per unit value, okay, XA is equal to 0.02. So this is the old value, okay, it's a given value here, and XB is equal to 0.04, okay, 0. But if per unit values are given, what we have to do here? We have to find out new per unit value. So let us find the new, here this is a per unit, okay, it is also per. So it is a per unit value, okay, per unit value corresponding to base kVA of, okay, base kVA of transformer A only, okay, transformer A only, okay. This is the per unit value, okay, per unit value corresponding to, okay, corresponding to the base value of, okay, base value of the transformer B only, okay, B only here. So that to get a common base value, we have to take common base. So that is that's why to the 2.2 per unit value. So let common base kVA, let assume the common base kVA is equal to, how do we get? You can take any value, base kVA. So that is the transformer A, the rating of the transformer A, the transformer A rating. So that is equal to how much? 800 I have taken, 800K. So this is a, okay, this is the new kVA ratings, like, okay, new. So now let us find out. So what are the new per unit value? So XA, the new value is equal to the XA, the old value, given value, so into kVA new, the divided by the kVA old, okay, kVA old. So now kVA XA old is equal to how much? 0.02. The into kVA new is 800 divided by 800. So now it is equal to 0.02 per unit 1. So next one, the XB new is equal to, okay, XB new, that is equal to XB old, okay, XB old, the into the kVA new, okay, divided by the kVA old, kVA the old year. So now this is equal to, so what is the value of XB new, okay, XB old year? 0.04. So this is the 0.04 into, so kVA new is equal to 800. So divided by kVA old is equal to 400. Now simplify this. 500, 500. Let's see what is the correct answer. First find, tell me XB new value here. What is the XB new? XB new here. Okay, that is a 0.08 per unit values. Okay, so now find out the load shared by the transformer A. Shared by transformer A. So that is equal to load KVA the into, okay, that is a XA XB divided by the XA plus XB values. Okay, XB new divided by, so XA new the plus XB new value. Okay, new only, don't take old values. Okay, what is the XB new value here? 0.08. So that is a 1000 kVA. The 0.08 divided by, so 0.02, okay, plus 0.08. So now simplify, they will get an answer. What is the answer? 0.08 divided by 0.02 plus 0.08. Okay, it is equal to 0.8. 0.8 into 1000. Okay, it is equal to 800 kV. Okay, so next one, the load shared by transformer B. So that is equal to the load KVA. Okay, here XA divided by XA plus XB. So now it is also equal to 1000. Okay, into XA is equal to 0.02 divided by 0.02 plus 0.08. So now it is equal to 200 kV. So this is the answer for this question. If the ZA ZB are given in the ohmic values like this, we have to find. Okay, so now solve one more question. Two single phase transformers are connected in parallel to share a load of 1000 kilowatts at a power factor 0.8 lakh. Rating of the transformer and their reactances are given as follows. For transformer A, 800 kVA, XA is equal to the 6%. For transformer B, 600 kVA, XB is equal to 8%. Find kVA shared by the each transformer. It is also similar to the previous question. How do we answer this question? Okay, first find out load KVA. Actually, here power is given in the kilowatts. Okay, here power is given in kilowatts. Load KVA is equal to the load power in kilowatts divided by power factor. So therefore it is equal to 1000 kilowatts, okay, divided by 0.8. So now what is the answer? 1000 divided by 0.8. 0.8. So that it is equal to the 1250 kVA. Okay, 1250. So now XA given that the XA is equal to 0.06 per unit. Okay, XB is equal to 0.08 per unit. Okay, so now let us assume here, let's assume Okay, the common base kVA, common base kVA, so that is equal to the kVA of transformer A, so that equal to 800 kVA. So therefore we can get the XA new is equal to, okay, XA new is equal to, that is the XA volt. So here no need to find, kV rating is both are same, so that is a 0.06 per unit. So next one, XA XB new is equal to XB new, so that is equal to the XB old value into kVA new divided by kVA volt. Okay, kVA volt. So now simplify, so it is equal to 0. That is the XB volt is equal to the 0.08 into the 800 divided by 600. Now this value is equal to how much? 800 divided by 600, okay, into 0.08. Okay, this is the first one. XB value is equal to 800 divided by 600, okay, into 0.08. So this is the 0.1066 per unit. Okay. Okay, am I right? This one, is it correct or not? So this value, tell me, is it correct or not? Verify. Yes. Okay, next find out after getting these values. So now here kVA shared by the transformer A. kVA shared by transformer A. So that is a load kVA, the multiplied by XB divided by XA plus XB values. Okay. So now load kVA is equal to 1250 kVA. Okay. This is the XB value is given. So this XB is equal to 0.1066 divided by 0.06 plus the 0.1066. Okay, by simplification this value is equal to how much? Okay, you will get this, calculate yourself. And kVA shared by the transformer B. So now this is the load kVA, the into XA divided by XA plus XB1. So this value is equal to 800 kVA, right? So now this value is equal to how much? It is a 1250 kVA. The into XA is equal to what is the value of XA? XA already we got, that is the 0.06 divided by the 0.06 plus 0.1066. So now it is equal to 450 kVA. Right. This is the answer for this question. Like this we have two answers. All of you clear now? So next one more question. Two single phase transformers are having same voltage ratio and no loads and operated in parallel to supply a load of 800 kilowatts. 800 kilowatts at a power factor 0.8. One transformer is rated at 400 kVA and has a per unit equivalent impedance of, this is the per unit impedance, and there other is a 600 kVA as a per unit equivalent impedance of, this is the impedance. So determine the load kVA on each transformer and power factors. Determine first one, what is the load kVA? Load kVA here. Here note in this case always here see, okay, lagging kVAR, okay, always in the any system, okay, in the system, any here in this, in electrical system, okay, electrical system, the lagging kVAR is a positive, okay, and leading kVAR reactive power, so it is always the negative. What is the reason? The inductive loads are more as compared to the capacitive load in the electrical system. That's why here lagging kVAR positive, leading kVAR is a negative. Similarly, okay, this is the similarly, okay, in this question, okay, lagging kVA, okay, lag in kVA is a positive, okay, leading kVA is a negative, okay, negative. So it is a very useful to find the power factors, okay, in this question. Okay, in the electrical system, lagging kVAR is a positive, leading kVAR is a negative. Similarly, lagging kVA here, that is apparent power, lagging apparent power is a positive, leading apparent power is a negative. Okay, so therefore first find out what is the load kVA here. The load kVA, okay, it is equal to, that is a, okay, at what power factors? So load kVA, load power in kilowatts, in the kilowatts divided by the power factors, so that it is equal to 800 kilowatts divided by 0.8. 800 divided by 0.8. So now calculate, this value is equal to 1000 kVA. Okay, 1000 kVA. So therefore load kVA is equal to, load kVA the is equal to, so now it is a 1000 kVA, okay, kVA. Now at an angle of, okay, it is a lagging power factor, so that is the cos inverse of theta. What is the theta here? So this is equal to the lagging, so that is a plus, okay, plus the cos inverse of 0.8. So now it is equal to 1000 kVA, okay, at an angle of the 36.86 degrees, okay, 86 degrees here. So here this is very useful, 36.86 degrees here. So now here also per unit values are given, okay, both are per unit values are given. So now let assume here, okay, in this case, the let common base kVA, the base kVA, the is equal to the kVA rating of transformer A, kVA rating of transformer A. So now this is is equal to, what is the kVA rating of transformer A? So that is a 400, okay, 400 kV, okay, 400 kVA one. So now simplify here, so that is the ZA new is equal to ZA new, so that is equal to the ZA volt, okay, ZA volt. So it is equal to 0.01 plus J 0.06 per unit volts, okay, per unit. So now ZB new is equal to How do we get ZB new? So that is a ZB whole, okay, ZB whole, the multiplied by KVA new, okay, it is a new KVA, okay, this one is a common base, means it is a new KVA rating. We have taken as a the new KVA rating, KVA new divided by KVA whole. So all of it clear? Okay, KVA new divided by KVA whole. So now simplify this. ZB whole is equal to, so what is the value of ZB whole? So now this is the 0.01 plus J 0.05, okay, multiplied by, so now this value is equal to load KVA magnitude point, your common base KVA here. So this whole new value is the 400, the divided by new value is the this is the new value is 400, old value is 600. Now simplify this, 4 by 6, okay, 4 by 6 only. So now it is equal to, calculate this one. Okay, calculate. Zero point, this value is equal to 0.015 plus J 0.09 per unit values. Okay, so we got ZA and ZB values. Okay, now load shared by the transformer A. Find load shared by the transformer A. Now find out load shared by transformer A. So how do we get load shared by the transformer A? So that is equal to load KVA multiplied by ZB by ZA plus the ZB values here. Okay, ZA plus Z. So now this value is equal to, okay, load shared by the transformer A. So now it is a 1000 kVA, okay, 1000 kVA at an angle of the 36.86 degrees, right? So now it is equal to multiplied by, so now this value is equal to, ZB is equal to, so now already we got this ZB new, okay, ZB new 0.015 plus J 0.09 divided by, okay, here ZA is equal to 0.01 plus J 0.06, the plus 0.015 plus J 0.09. So now calculate, simplify this equation. So you will get the load shared by the transformer A. Anybody got it? So simplify this, convert into the polar form. Then finally you will get here load shared by the transformer A. So this is equal to 358, okay, 0.54 at an angle of 38.045 degrees. Okay, 045 degrees here. So this is the load shared by the transformer A. Have we got it, Nageshwar? Very, very important formula for the gate point of view. Next one, load shared by the transformer. Yes, that's correct. Very good. Load shared by transformer B. Okay, load shared by the transformer B. What is the formula here? Load KVA the into ZA by the ZA plus the ZB. So it is a load shared by the transformer A, load shared by the transformer B. So now ZA plus ZB by. So now simplify here. So that is the 1000 okay kVA at an angle of 36.86 degrees. The into ZA is equal to, so it is a ZA value is equal to 0.01 plus J 0.06 divided by, okay, ZA is equal to 0.01 plus J 0.06 the plus, okay, J 0.015 plus J 0.09, J 0.09. Now simplify this. Okay, now simplify this value. What is the answer for this case? You will get magnitude as well as, okay, this value will get 641.57 at an angle of 36.1976 degrees. Okay, so now these are, okay, this is a, okay, this angle indicates here, okay, this angle indicates that is a power factor angle, okay, power factor angle for transformer A, okay, transformer A. So this is the power factor angle for transformer B, okay, transformer B. So now by using these angles we can find out the power factors. Okay, so now therefore the power factor of the transformer A, okay, power factor of the another one, power factor of transformer A is equal to, so that is the cos theta A. So cos of, what is the angle here? So this angle is equal to the 38.058 degrees. Okay, 38.058. Okay, 38.045. 38.045. So now simplify this equation. Cos 38.045. Cos 38.045 is equal to 0.787. Now tell me, is it lagging power factor or leading power factor? Pawan, now tell me, is it a lagging power factor or leading power factor? I already mentioned here. Okay, if the lagging kVAR is a positive, leading kVAR is a negative. Suppose if angle is a negative, okay, if angle is a positive here, that is a lagging. Okay, here we have taken lagging. So why I have taken places for lagging kVA? Okay, lagging kVA here. No, here. Here that is the leading. No, it's not leading. Lagging kVAR is positive. Yes, both are lagging. Why we have to take here? So due to positive angle of, okay, due to, so this is the lagging only, okay, lagging. So why? Because so due to positive angle of the kVA, angle of the kVA, that's why we have to take lagging. So next one, power factor of transformer B, that is the cos of theta B. So that is equal to cos of what is the angle? 36.1976. 36.1976. Okay, it is equal to how much? So this value is equal to anybody got it? 0.806. 0.806 lagging only, not the leading. What is the reason here? Because of positive angle of the kVA. Okay, so this is the problems based on this concept. So there is a one more question. Can you solve, or let us stop? There is a only one model. What's your question? Here X by R ratios are equal. I think X by R ratios are not equal here. X by R ratios of the transformer B, X by R ratios of the transformer B. It is a ohmic values. X by R ratios of the ohmic resistance of X by R ratio is equal to ohmic resistance of the X by R ratio are equal, then power factor is remains same. Okay, now can you solve this question? Two transformers A and B connected are in parallel to the same load. Open circuit voltage of transformer A 6600 and for transformer B A is equal to 6400. Equivalent impedance in terms of the secondaries. Okay. So okay, solve this question yourself. It is like homework problem. Let us stop this session. It is a time over. Homework. Okay, solve yourself. If you have any doubt, we will discuss in the next session. If you have any doubt about this question, we will discuss in the next session. Okay, next lecture. Okay, solve yourself this question. This is the question based on the unequal voltage ratios. Okay, here what are the questions here? I will tell you the questions. Determine following. Okay, first one is terminal voltage. Second one is current of transformer A. Current of transformer A. Next one, current of transformer B. Okay, so and next one, the active power shared by transformer A. Shared by transformer A. Sorry, power shared by the transformer A and transformer B. And also power factors of transformer A. Power factor is not required here, so up to the power calculate. Yes, that's why I'm giving homework problem. So find these values VT, IA, IF and all these values. So tomorrow we'll discuss about this question. Okay, remind this question. I will discuss tomorrow this problem. So clear my point? Today we have discussed a complete concept of the parallel operation of transformers. Okay, what are the necessary conditions? What are the desirable condition? How does load shared by the each transformers? So in the both two cases, when voltage ratings are equal, when voltage ratings are unequal. Okay, very important concept. There is a possibility to get the question from this concept. Do you have any doubt about this concept? Please mention in the comment box. Okay, Nageshwar, all of you got it? Any more doubts about this concept? Okay, shall we stop the session? We'll discuss with a new topic tomorrow. So this is Unacademy GATE schedule. I am teaching electrical machine from Monday to Friday 4 to 5:30. Okay, and same at the same time communication system Nageshwar sir is teaching 4 to 5:30 Monday to Friday, and Venkatakrishna sir is teaching engineering mathematics Monday to Friday 7 p.m. to 8 p.m. Geometry class. Okay, Sharma sir is teaching this class. Okay, now it is a timing is 8:30 p.m. to 9:30 p.m. Okay. And it is official creatrix channel. Okay, you can solve yourself. Tomorrow we'll discuss that problem. The calculation part is there, so that's why I'm giving homework. And also time is off. Actually our timing is 4 to 5:30, but now nearly 6:30. 1 hour is a extra I have taken. Okay, it is official. This one is the Unacademy GATE Telugu channel. For any updates from the Telugu team, please join in this group. Okay, it is different type of channels under the Unacademy. One is the creatrix GATE. Okay, mechanical, civil, GATE Telugu, SSC, JE, computer science, GATE questions, Unacademy GATE questions, electrical junction, Unacademy engineering foundation, engineering Pathshala. So this is our channel. Please like and share, subscribe this channel. Okay, thank you all. Thank you very much. Tomorrow topic is a harmonic analysis of or effect of harmonics of three-phase transformers. Effect of harmonics in the three-phase transformer. Okay, this is also very important. Tomorrow we'll discuss this topic. Okay, thank you all. Thank you very much.